Thank you, Edson. Thanks everyone for joining. Yeah, the topic of today is HVDC cable rating calculations. It's going to go for 1.5 hours. So, who is ELEK Software? Well, we are a team based in Sydney, headquartered here, but we're also a distributed team. We've been developing power systems design and analysis software since 2009. We have thousands of users using our software in many countries. We have three main products: ELEK Cable Pro Web for low voltage electrical design, Safegrid Earthing software for finite element analysis of earthing systems, and ELEK Cable HV for HV cable rating calculations. We have a lot of different, high profile users from, Siemens, GE, etc. Using our software down to all sorts of different companies, small and large. So we develop the software and we fully support it from Sydney. As Edston alluded to, some of the contents of this presentation, this is not everything, but I will cover why you should choose or why the reasons for choosing HVDC cable systems, HVDC versus HVAC, which is very interesting in terms of capacity, HV cable system configurations, design considerations for HV cable systems. I will provide a full list of IEC standards that you might want to refer to and a full list of relevant C-grade technical guides as well. You could take a screenshot of those slides. It might be useful for you. I'll provide the formulas for HVDC current ratings and explain those. I'll talk quite a lot about electric field and field inversion and how it's also interrelated with insulation temperature drop. Like I mentioned, there will be up to five worked examples or live software demos in this presentation to keep it really interesting and practical. Finally, I'll draw some conclusions and provide recommendations. And then we will have a Q&A session based on the questions that you type into the chat. So please keep the questions going. Edson will probably answer a few of them as we go, and we'll keep them till the end. ELEK Cable HV software is powerful, accurate and validated software for cable current rating calculations. That's the software that's being used for the demonstrations and for the modeling results that you're seeing in this presentation. It's suitable for any AC voltage and HVDC cables. HVDC ratings require a little bit more than HVAC, and we'll see why. It complies with IEC 60287 standards, which is the main authority for cable rating calculations. There is also the finite element method, which is used when you need to model installations beyond the IEC limitations. It can perform current rating calculations for your custom cables based on your cable manufacturer data sheets under your specific installation conditions. It's accurate and it's validated. There is a very wide range of installation conditions that are covered along the top there. You can see the modules, and you can get a free 14-day trial within minutes, actually. You don't need to download or install the software. If you're interested in a free trial, just go to elek.com and navigate to the ELEK Cable HV software page, and you can get a free trial within a few minutes. So let's talk about HVDC. Why choose HVDC cable systems? Well, in general, HVDC transmits more power per conductor than AC due to the absence of reactive power and no skin effect, for example, on the conductor. HVDC cable systems are therefore ideal for very long underground or submarine routes where AC becomes impractical due to high charging currents or capacitance. Fewer cable conductors for HVDC reduces the easement size. HVDC systems enable the interconnection of asynchronous grids. However, converter stations still present a significant challenge in terms of their site placement, the land use that they require, and their increased complexity, and of course, their quite high costs. Here's an example in the photo of a real cable tunnel that uh, includes HVDC cable system on the right-hand side and two HVAC circuits on the left-hand side in China. Here's a high-level example of HVDC versus HVAC cable current ratings. So for equal power ratings, or there is a power requirement, DC cable systems are significantly cheaper. We're talking about the cable systems, or the cables and the installation costs than comparable AC cable systems, excluding the converters. So here in the top, so if we needed to achieve a particular power delivery um, of perhaps above 1080 MVA. So you've got the HVDC circuits in the top right, two cables, quite a tiny easement, conductor size 2000 square mils. And then there's the equivalent AC 400 kV HVAC circuits, so two circuits with significant separation required for mutual heating between these two circuits. There's a greater number of cables required for HVAC to deliver the same power, and you require a significantly larger easement, so more property. And as we know, property cost is very significant. So that gives you an idea of why HVDC power delivery is so attractive, HVDC cable. Let's talk about the different HVDC cable system configurations. So we've got the asymmetrical monopole, the symmetrical monopole, and the bipole system. Asymmetrical monopole, it involves a single HV cable and a single earth or metallic return conductor, be that a dedicated conductor or the earth itself. It provides lower cost, but it has no redundancy. The voltage utilization is either a positive voltage or a negative voltage for the power delivery single HV cable. And it's typically used for short length or where cost is critical or a limiting factor. Then we've got the symmetrical monopole. That involves two HV cables with a plus and a minus voltage cable. No ground current, therefore no earth return is required. It's economical for lower power delivery. Unfortunately, there's no redundancy. So outage of the total system if either cable fails. Typical voltage level of up to 400 kV and a max rating per circuit of around 750 megawatts. Then we have the ideal or bipole system, which these days especially for important HVDC links, it's the most popular. Consists of two HV cables and a metallic earth return conductor. It has redundancy. So if one pole fails, then it can still deliver 50% of its capacity. Of course, it has much higher costs, uh, but it utilizes double the voltage level of a monopole system. Therefore, it can deliver much higher power levels at much greater voltages. But again, the cost is significantly higher for not only for the cable systems, but also for the converters. So you can see in the bottom, there's examples of the required HV and, well, the earth return conductors for the asymmetrical monopole in the bottom left and the bipole system in the bottom right. So typically the medium voltage cable there shown there for the asymmetric monopole is used as the earth return conductor. And the bipole system requires a significantly smaller dedicated earth return conductor because the earth return currents are significantly less than compared to an asymmetric monopole. Design considerations for current rating. These are common for AC cables with a little bit of difference. So conductor design, so you can consider that there's no skin effect in DC, which allows for compact circular conductors. Water blocking features of these cables are essential for reliability. I mean, these circuits are expensive and they're extremely important. Uh, so and especially if they're underwater, water blocking for reliability is extremely important. The insulation thickness is a very important factor, and it's determined by the electrical stress requirements, the space charge, but not just voltage. It's manufacturer specific based on experience and installation conditions. Dielectric losses are negligible for HVDC cables. So in general, the conductor losses are reduced. The insulation dielectric losses are reduced, leading to greater power capacity for HVDC. Sheath bonding, circulating and eddy current losses are negligible to non-existent. Regular earthing of the armor, the sheath, the screens for HVDC cables, if they so exist, is required at every 6 to 9 kilometers as a rule of thumb to manage transient voltages. And then the typical installation factors such as burial depth, soil thermal resistivity, and proximity or mutual heating between other cable circuits is also very important. But that also applies to HVAC. But you'll see the impact of the installation conditions on the electrical stress limits, and the thermal limits for HVDC cables, which is very interesting and what we will be discussing quite a lot in this presentation. Here's a slide of real practical. So if you're doing a design that involves HVDC, these are the IEC standards that you should be referring to and following and including in your reports. So if I were you, I would take a screenshot of this one. Now the IEC 60287 series does not directly provide a method for calculating HVDC cable rating calculations. You need to modify those methods or equations to be able to deal with DC voltages above 5 kilovolts. So that's HVDC. And here is a list of the relevant C-grade technical brochures related to HVDC cable projects. Yeah, they're all relevant, all useful. The last one is in progress. It's not released yet. That's related to grounding aspects of HVDC, which is not well covered anywhere really. So in HVDC cable rating calculations, there are two limiting factors, not just one, such as for HVAC. Now we're talking about two limiting factors, be that the thermal limit and the electrical stress limit when we're dealing with cables, DC cables above 5 kilovolts. So that relates to the dielectric field inversion phenomenon. We're talking about the stress limit. The thermal limit is common and should be well understood from IEC 60287. The field inversion phenomenon is affected by the operating voltage and the current loading. So the current loading affects the electrical stress. Mm. And this field inversion phenomenon can lead to dielectric breakdown due to high electric stress on the insulation, particularly on the outside or the external surface or the outer diameter of the insulation layer. So what happens in the bottom left-hand corner plot there, you'll see under different load conditions of a HVDC cable. So as it carries more current, the uh, the field inversion or the space charge phenomenon occurs, and electric charge accumulates, moves and accumulates to the outer edge of the insulation. So moving from the inner insulation to the outer insulation. So the peak electrical stress occurs at the outer insulation, leading to the electrical stress limit. So in the bottom right-hand corner, you'll see another plot where a cable, depending on the operating voltage, now it's not only dependent on operating voltage, this is simplified, but you'll see at different operating voltages, a cable can, HVDC cable can either be thermally limited or it can be stress limited. And the the ultimate or the overall rating is the lower of the two. So there's always a thermal limit and there's always a stress limit. And the current rating is the lower of those two values. Here is the formula for HVDC cable current ratings. Okay, the top equation. It's much simpler for DC cables compared to AC. If I show you the equivalent one for HVAC, it has many more terms, because we have to deal with the electrical losses in all of the different and metallic layers. But with HVDC, we don't have to. But now we really have two equations. We have the thermal constraint equation, that's the top equation, and then we have the electrical stress constraint equation. The electrical stress constraint it's the additional equation. You won't find that in IEC 60287. That is related to, or it's related to electrical losses. So WC, so electrical stress is dependent on the electrical losses in the conductor or the loading, current loading of the conductor. It also depends on the dimensions of the insulation, the inner and the outer radius or the thickness of the insulation. And it's interrelated to the temperature drop across the insulation. Now, I'll be explaining this in subsequent slides, but it's the temperature drop across the insulation as the cable heats up, which changes its electrical conductivity of the insulation, which leads to this space charge effect or the movement of charge within the insulation from the inner or from a uniform distribution to an accumulation on the outer side of the insulation, leading to this increased electrical stress. So both these equations are used for HVDC current ratings. Let's talk about electrical field distribution in HVAC cables, and then we'll talk about it for HVDC. It's important to understand the difference. So for HVAC cables, electric field within the cable depends on the cable geometry and the insulation permittivity. The field peaks at conductor surface, so the inner of the insulation, and decreases towards the outer layer of the insulation, towards the sheath, right? Field distribution is stable and set by geometry for a given operating voltage. It's called capacitive grading as it matches a cylindrical capacitor's field. Here's the simple equation for electrical field within an AC cable with respect to the radial distance. So from the conductor to the outside of the insulation. You won't see permittivity in this equation, but it does apply. It's because it cancels out. Let's talk about the difference. Now, electric field distribution in HVDC cables is referred to as resistive grading. And as you can tell by the equations, it's quite a bit more complicated. In HVDC cables, the electric field evolves over time based on insulation resistivity. Initially, it's capacitive, and the field redistributes due to leakage current. Steady state fields depends on conductivity, not permittivity, as was seen for AC cables. The field is highly sensitive. The electric field within an HVDC cable is highly sensitive to temperature and material properties of the insulation. Field inversion can occur. That's where the maximum electrical stress shifts towards the outer insulation. Now in HVAC, we're used to the maximum electrical stress occurring at the inner of the insulation, but as field of inversion occurs, it moves from the inner to the outer. As I mentioned, the equation here is quite a bit more complicated. There are more interdependent terms here. So we've got an electrical stress with respect to conductor or insulation radius here. Ri is the inner radius, Ro is the outer radius dimension. We've got operating voltage there, U, and we've got WC for conductor losses. So electrical stress is dependent on the conductor losses. And the bottom equation, we can relate WC to the temperature drop across the insulation. So I'll just summarize by saying that temperature drop within the insulation affects the resistance of the insulation or changes the resistance or the conductivity, I should say, of the insulation, which leads to this space charge effect. So let's talk about field inversion. As I've already mentioned and shown you, uh, the steady state, so after the initial phase, the steady state electric field in DC cables is resistive. And so it's fundamentally different compared to the capacitive field of AC cables. So it's resistive and it varies with temperature. So the DC electric field strongly depends on the temperature difference across the insulation due to temperature-dependent conductivity. The insulation temperature gradient or the temperature drop, so from at the inner insulation layer, you'll have a higher temperature and temperature reduces towards the outer layer of the insulation or the outer edge of the insulation. So you've got a temperature drop. And that changes the conductivity, the temperature of the insulation at a particular location or radius changes the conductivity. So the insulation temperature gradient or the drop causes the space charge accumulation, which modifies the electric field distribution. A higher temperature drop can result in field inversion, where the field is higher at the outer layer of the insulation and lower at the conductor. So in this plot here, we can see three different cases. So the orange curve is electric field strength or intensity starting from the inner layer of the insulation to the outer, right? So you've got electric field, it's same as AC. Under no load, you've got higher electric field at the inner and lower at the outer. Now, as we load the HVDC cable, we get this temperature drop across the insulation, and that can vary the electric field until we get this field inversion. That's the blue curve, right? We have this significant field inversion, which corresponds to a temperature drop across the insulation. Now we need to be very careful with because these cables obviously have an electrical stress limit, and that's related back to this temperature an equivalent temperature drop limit. In this case, the temperature drop limit for this insulation, as per this plot, is 10.7 degrees Celsius or Kelvin. So how do we model HVDC cables? So let me provide some general guidance. It's actually much simpler to model uh, the cable itself. They're generally much simpler cables. They will almost always involve an armor layer. But we still need to properly model these cables for thermal and electrical reasons. So we should be using a cable manufacturer data sheet, and then we should be referring to the IEC standards and any relevant C-grade technical brochures or guides for the material properties. Within our software, we have all that inbuilt, all those material properties. And you should follow the guidance provided by C-grade technical brochure 880, for example, that tells you to prioritize diameters over thicknesses. If there's any discrepancy um, what happens quite a lot with these data sheets is there's discrepancies between the dimensions, and you should prioritize any diameters, cable layered dimensions according to diameter as opposed to thickness. Avoid combining layers. You should model layers, all of the layers separately within your cable model. And we allow you to add custom layers if necessary. Here's an example model of a HVDC cable. Uh, so it has a double armor layer. It's a submarine export cable rated at 320 kV DC. It's a single core cable with a copper conductor of 2000 square millimeters. Now, importantly, what you also need is a maximum permissible temperature drop across the insulation if you're going to properly rate this HVDC cable. Now, so you'll need that temperature drop limit, and it varies quite a bit. Sometimes it's not even given by the manufacturer, but you really need it. So you should obtain the temperature drop limit for the insulation from the manufacturer. If you can't, you can assume an electrical stress limit, and our latest software, which I think Edson is going to demonstrate, allows you to enter a maximum permissible electrical stress limit in kilovolts per millimeter if you don't have this allowable temperature drop limit from the manufacturer. So I think I'm going to hand over to Edson now, and he's going to show you how to model a HVDC cable using software from scratch from a manufacturer data sheet. Then we'll continue with lots more technical slides. So I'll hand over to Edson now.
Hello everyone. What we are looking at to model today is an example from TB880. It's a 320 kV HVDC submarine bipole cable. I've just highlighted the important parameters what has been given in that document. So it's a 2000 square mm copper conductor. It has a lead sheet. It has a double armor. The maximum temperature drop for this cable is said to be 10.7 across the insulation. And the maximum conductive temperature attainable is 70 degrees. Now, this 10.7 K is what Jason was talking about, the maximum temperature drop across insulation. Very seldom it's very difficult sometimes to find this number of 10.7. So in our latest release, in the next release of Cable HV, we will have an option to enter the stress too, so that you can get the temperature from the stress. Now, this document also gives you the data sheet for this cable with all the materials required to model this. So let's see how we can do it in our software. So I'll just keep it side by side for easy following. So this is the Cable HV software. So you would see that we have many installations and some modules attached to it. Let us go to the cable modeling section of it. So we can add our cables or systems in the cable system navigator. I already have a cable here by default. but I will start to make a cable from scratch and add it to the system. So I go to a new system. So I bring up the cable model the cable model developer. So it's a cable, I just give any description I like, for example, a 320 kV DC cable or HVDC cable. We do that. The cable type, we have several cable types, but this is an HVDC cable. So I go on with HVDC. It's a single core cable. It's a DC cable. The voltage is 320 kilovolt. So I enter that. I can enter any nodes that I want. If required, I can enter the nodes and they will be printed in the report as well. The next one that we're talking about, the most important part, is a conductor. Now, in this cable model, we have a copper conductor which has a diameter of 51.6 mm. So let me enter the diameter here. Uh, as we discussed earlier, the conductor size is 2000 square mm. So I selected from the drop down. It's a copper stranded conductor. So I have it. All of the parameters are discussed in here. So we calculate the standard DC resistance from the standard, and that will be shown here. The next element that we have is a conductor tape. It's a semi-conductive tape with 52.9 as the outer diameter. Now, these layers are what we call as custom layers. They are not the standard. There may be custom layers added. So to add a custom layer, after any layer, we select the corresponding layer and then press insert. So we have a new custom layer formed. I can give it a name here. For example, I can call it as a tape because it's a conductor tape. The diameter is going to be 52.9. The material said is going to be a semi-conductive material. We have a list of materials here which you would like to select. For example, if I want a custom material, let me cut this as custom material. And because it's semi-conductive, as per guidelines of TB880, it is 2.5 is the thermal resistivity. So I enter that value. The next one is a conductor screen. It's also a semi-conductive material with a thickness of 2 mm. So there's a conductor screen here. The thickness is 2 mm. Because only thicknesses are given, we can use thicknesses, but in case diameters are given, we always prioritize the diameters. So the material is semi-conductive, so it's already selected here for me by default. The next layer is the insulation. So that's the most important layer here. So the insulation thickness is set to be a 16. So let me use the thickness here. The maximum operating temperature, as we discussed earlier, for this material was 70 here, and 10.7 is the temperature drop across insulation. So now in the latest version of our software, what we have is, sorry, we can enter 70 here. Yeah. Now in the next release of cable, what you see is you have two options: either to enter the temperature drop across insulation, which is 10.7, which is already entered here, or the other one is you can calculate temperature drop based on electric field limit. So I can, for example, select this parameter and then select what is my field limit if that information is available, and then a corresponding temperature drop is automatically calculated for us. So either way, you can either enter the temperature, get a stress or stress limit, or enter the stress limit and get a temperature from it. So both these options are available. I will just go with the current option of 10.7 as per TB880.
Looks like you're using an unreleased version of CHV, ELEK Cable HV.
Yes. Just
Yeah,
to show these parameters.
yeah.
Yeah. The insulation type is an XLP insulation, and it is unfilled, greater than 18 kilo or 36 kilovolt. Always use unfilled. If you are not sure, always use unfilled for XLPE. The next one is an insulation screen, which is also a semiconductive polyethylene with 1.5 thickness. So insulation screen is here. The thickness is 1.5. And it is a semiconductive material. I don't have to it by default, but if you want a custom material, you are free to go ahead and add this. The next one that we have is a semiconductive tape. Um, it is the thickness is not given, but the diameter is given here. So let me add it as a custom layer. A semiconductive tape. The diameter is 93.5. So I'll just enter the diameter. The thickness will be automatically calculated. It's a tape. I'll just call it as a tape again, or the second tape. Because it's semiconductive, let me use custom and enter the thermal resistance as 2.5. If it's any other material, you are free to add any material that you want from our database. The next one that we have is a sheath, which is a lead alloy, and the thickness is 2.3. So we have a sheath material here. You can select the sheet material. It's a non-corrugated sheet. The sheet diameter, the thickness is 2.3. So I'll enter the thickness 2.3. Diameters will be automatically calculated. It's just a lead tape without any tape, lead sheet without any tape. So I just add the lead tape. All the DC resistances would be calculated from there. The next layer I have is a protective sheet or like a water blocking tape. So let me add another tape here. It's another tape. I'll call it as tape 3. It's again a semiconductive tape. The diameter, the thickness being 3.1. So I can enter 3.1 and select 2.5 as the thermal resistivity because it's again semiconductive. The next one I have is the armor bedding. So this is a double armored cable. So I have two armor beddings and two armors. So let me add a armor bedding here. The armor bedding is again a semiconductive bedding. So again, I can go with semiconductor materials, which have 2.5. The diameter is 104.6. So 104.6. That's it. The next one is the armor, which is a galvanized steel wires. Now, if you see a DC cable, we will not have many information on the armor wires because the losses are negligible. But in AC cables, you will require the number of armor wires, the lay length, etc. So in here, in this example, they've just given the outer diameter of the armor, or sorry, thickness of the armor wires, which is 2.5. So let's put the thickness as 2.5. The material is steel already here. The number of armor wires is not specified, but mostly it'll be almost 40 to 50 armor wires. So we can just enter for design lay length. If you know it, you can enter it, but it's not very important DC cables because losses are negligible. The next layer we have is again again another armor bedding, which is 110.4 in diameter. So I can add the next armor bedding with 110.4 as a diameter. It's again it's a plastic tape, a plastic nylon tape. So I can use a PVC tape here, which is greater than 35. That will be good for this. And then going back to the armor 2, again a second armor, again galvanized steel is here. The I think it's 2.5 in thickness again. We go on with that. The number of wires again 50. And the last layer we have is an outer serving. So it's the jacket that we call. You could keep on adding any layers that you want. The thickness is 4 mm here. So I can use it as 4 mm. The outer serving is PP yarn, which is polypropylene yarn. So I can select it from this. If there's any other material, you can do it from here. So this comes up to 123.4, which is the external diameter of the cable. So once the design is completed, you could either save it and use it in many projects, or you can exit it. You can specify the points of bonding because you want to avoid transients. And then we have another system too, which is already here. So you could add this in any of these installations and do your calculations.
So let's talk in more detail now about insulation temperature drop versus electric stress. So the maximum electric stress experienced by the cable varies with insulation temperature drop. Insulation temperature drop is depends on the loading of the cable. So this plot here shows different insulation temperature drop versus the maximum electric field experienced by the cable insulation, be that on the inner or the outer uh, radius of the insulation, for want of a better term. So as we go from what we term as, so before field inversion occurs, we're on the left-hand side. So we've got the sloping curve uh, from the left-hand side to the right. Hmm. Uh, as insulation temperature drop increases, the maximum electric field experienced by the cable reduces up until field inversion occurs. And when field inversion occurs, that phenomenon that I've been talking about, the E max or maximum electric field uh, that affects the cable insulation increases significantly. Now, it's also different depending on the operating voltage. So we've got lower maximum electric field strength for the 320 kV HVDC cables compared to the 525 kV cables if you're looking at the plot there. We can also see that as conductor size increases, the electric fields, maximum electric field experienced by the cable increases along with operating voltage. Now, importantly, thinner insulation also causes the HVDC cable to experience higher electric field strength. So you can effectively increase the electrical stress limit or increase the current capacity in certain cases if just by increasing the thickness of the insulation. So you could work with the manufacturer on that perhaps. So there's a point here that cables with thinner insulation for the same operating voltage experience higher electric field and hence lower current ratings. And there's a very big difference. So 16 millimeters thick insulation compared to 20 millimeters triples the electric field difference or electric field intensity. Transmission capacity. So HVDC cable systems have very high transmission capacity, but it's voltage dependent. So actually transmission capacity of HVDC circuits can peak at voltages below the cable's rated operating voltage, which is very interesting. Under thermal limits, capacity increases linearly with voltage up until the stress limit is reached. So under stress limits, so you can see that linear curve from left to right as operating voltage increases and transmission capacity is increasing with operating voltage. But once we reach that electric stress limit, then transmission capacity significantly drops off as we increase operating voltage. It's quite counterintuitive to what we're used to with AC systems. So the electrical stress limit or Emax has a significant impact on transmission capacity. So therefore higher Emax, higher electrical stress limit shifts the peak capacity to higher operating voltages and increases capacity. So HVDC cables have with a higher Emax limit can achieve greater transmission capacity. They become stress limited at a higher operating voltage. Now we're going to look at a worked example, an unfilled trough installation containing a single HVDC circuit. So I'm going to hand over to Omer.
Thank you so much, Jason. And, Edson had just has shown you the glimpse of our software, what it can do in cable design. Once you design your cable, there are many interesting things you can do. And in these short demos, he will demonstrate what factors affect HVDC current ratings and when the current carrying capacity of HVDC ratings uh, is limited by thermal constraints and when is it stress limited. So we have created the project with practical examples already, but you can easily create project by going to new project, or if you have the project, you can open project from here. And regarding cable selection, you can go and select the cables from here. You can create cable or select the cable from the cable database, one of the cables, and then load the cables and
Okay, so Omer,
then
so so what cable system is in this model here now? So it's a HVDC circuit, right?
Yes, in this cable, in this model, we are using HVDC 1000 square copper cable that we have in our CHV software.
Yeah,
And
we have a new database of HVDC cables. I don't know how many we're adding, but I think it's hundreds perhaps
yeah,
of different voltage levels. Let me just follow it through with you. So this
yeah,
HVDC cable has a maximum allowable conductor temperature of 90 degrees.
yeah.
Now so what are you going to demonstrate? What are you going to vary? Or what
Uh,
can you tell us about what we're seeing now as in terms of the rating
yeah.
in that unfilled trough?
So, uh, so in this case, we have an ambient temperature of 20 C and unfilled trough, which has parameters set according to the Segre TB880 case study. And at 20 degrees C, and with these parameters, we can see that the cable is stress limited, which is indicated by dictating factor uh, value to be true, which is temperature drop across insulation. And
So
if you go
so
to,
so we need to explain this. So we've got a little indication there that the dictating factor for this current rating of 1290 amps is the temperature drop across the insulation. So that indicates that the cable is electric stress limited. And we can see that on the installation diagram, you can see the current rating 1290 amps, and you can see the conductor temperature there. It's actually operating below its limit of 90 degrees. It's operating only at 70 degrees Celsius. The conductor is operating at below its thermal limit. Therefore, it's
yeah,
stress limited, right?
yes, yeah.
Okay.
So this represents 20 degrees C. It represents a cooler climate. So if, for example, you have a system installation in a hotter climate, we change it to 40 degrees C. And now the temperature drop across insulation is no longer the dictating factor. So now your cable has become thermally limited, which you can see the temperature has reached 90 degrees C. So your
So we
cable is
did
now,
we didn't it was like 1290 amps compared to 1250 with a 20-degree ambient temperature difference. So like we
yeah,
didn't get um it didn't reduce the current rating by much by increasing the ambient temperature by 20 degrees. So
yeah,
the electric stress limit is significant, right? It
yeah,
significantly limits the cable in the first
yeah,
case.
yeah.
Is there anything else that we can show, Omer, for this case? Or not really?
Uh, well, not really in troughs because the current ratings change very slowly with wind speed
Yeah,
and wind
yeah,
speed
yeah.
also. So
We
I
can
think in
vary
troughs,
some.
ambient temperature becomes a big factor.
Yeah, yeah, yeah. So
We
when
would have
we,
more cases for buried
yeah,
when we
yeah,
go to buried.
yeah, yeah, yeah. But we're effectively switching the rating of the cable from being stress limited to thermally limited when we change
Yeah.
when we change the ambient temperature. Okay, so I think
Yes.
we'll continue with the presentation and we'll
Yes.
come back to another example, right, of buried, yeah?
Yep.
Thanks so much.
Thank you.
So in general, so unfilled troughs relate to cables in air. So if we have HVDC cables in air, there's a lot of detail in these plots. We put a lot of effort into it. So let's talk about varying conductor size. It makes obvious sense that increasing conductor size obviously increases the current capacity of these HVDC cables significantly. Insulation temperature drop as well decreases with conductor size. And due to the lower temperature drop limit, the higher thermal resistance between the conductor and sheath T1. So I think interestingly, from this plot is that a higher rated uh, cable operate a cable operating at higher voltage, so 525 kV, actually has a lower current rating than a 320 kV HVDC cable. And and that's caused by the electric stress limit. So the onset of electric stress limit occurs much earlier at 500 kV compared to 300 kV. So it was quite interesting to see that the current rating of a 500 kV cable is lower than a 300 kV cable. However, of course, the transmission capacity of a 500 kV cable is going to be higher, right? But the current rating is lower. I'm talking about comparing 320 kV with 500 kV. Ambient temperature, we're still talking about HVDC cables in air. Obviously, you increase ambient temperature and you can affect the current rating, as we saw even in the unfilled trough installation. So thermal ratings drop with higher ambient temperatures. So you'll see a crossover point. So here on this plot, so for example, the two red plots there, right? So you've got the stress limited rating and the thermal limited rating. And remember I said it's for a particular ambient temperature, it's the lower of the two which dictates the current rating. So as we increase ambient temperature, we start with the stress limit on the bottom. As we increase ambient temperature, the cable becomes thermally limited. The HV cable becomes thermally limited, and the thermal limit dictates the current rating. Now we're showing this for different conductor sizes. So as ambient air temperature increases, cables with smaller conductors are more likely to be thermally limited. As opposed to larger conductors, cables with larger conductors are more likely to remain stress limited. So the electric stress limit is dominant at low ambient temperatures. So colder climates, electric stress dominates. Hotter climates, the opposite. Electric stress rating is quite relatively stable across varying ambient temperatures, but the thermal limit is significantly varies. Still talking about cables in air, so electric stress limit, let's talk about that. So HV current ratings are highly sensitive to maximum electric stress. Insulation has a rating for maximum allowable or permissible electric stress, and it's hard to know exactly what that value is, but C-grade provides technical brochure 852 provides some guidance. There is lots of varying information, but let's say in general, we are talking about 20 kV per millimeter as the electric stress limit for HVDC cable systems operating below 400 kV. And it could be something above 20 kV per millimeter, stress limit above 400 kV. But stress limits vary. I'm talking about XLPE insulation there. Stress limits vary by insulation. Look, it's again, as I say, it's hard to exactly pinpoint a value. The literature is all over the place. But for mass impregnated insulation, there's a higher insulation, maximum electric insulation stress limit of 30 kV per millimeter. Now, what we see in this plot is a significant difference. If you assume that the electric stress limit on a HVDC cable insulation type was 18 kilovolts per millimeter compared to 20. If the cable is electric stress limit, look at the variation in the current rating. A small difference in electric stress limit, that assumption significantly varies the current rating. Now be careful, what I've seen is in manufacturer reports or values where they've provided this stress limit or an equivalent or corresponding temperature drop limit, they're quite lax in that value or relaxed. And I think that if you work with them to get an accurate value for this limit, you can significantly increase the capacity of your HVDC system if you so need. I've seen a wide variation between manufacturers. Let's look at another example of a buried HVDC cable system and how varying different installation conditions changes the rating. I'll hand it back to Omer.
Yeah, this is a very interesting case. We can vary many parameters in this case. This is a buried case, and we would see how the depth, variation in depth, pole separation, having ducts as opposed to not having ducts or soil drive affects the HVDC current ratings,
So,
whether they are
Omer,
stress limited.
Omer, just
Yeah,
quickly, so it's clear. It
yeah.
looks like it looks like the insulation, maximum allowable insulation temperature is 70 degrees, not 90 for this cable.
Yeah, I
Because,
was just going to talk about the cable. The cable that we are using in this case is the case 7 TB883 20 kV cable that the Adston had just shown you. He had just created the cable for. So this is the same cable. This has a maximum temperature of 70 degrees C and insulation temperature drop limit of 10.7 K.
so 10.7 degrees Kelvin corresponds to, what do you think that corresponds to in terms of electric stress limit?
So it corresponds to an electrical stress limit of 21.28 kV per
Uh-huh.
mm.
Uh-huh.
So yeah, which is in the same ballpark figure. About 20 kV per mm is what is reported for XLP in most cases.
But if you assume 20 kV per millimeter, then
Yeah.
the corresponding allowable temperature drop limit would be something below 10.7, is that right?
Yes, that would significantly be below. That's why it is really important to know the exact limit. Even a small change in even 1 kV per mm change
Yeah.
can significantly affect the temperature drop limit. So this TB880 case has an ambient temperature of 15 degrees C and thermal resistivity of 0.8 km per watt. And so we start with cable separation of zero point 0.3 at 2 meter depth. And you can see the dictating factor here. Temperature drop across insulation is not the dictating factor as it is set to false, meaning that the cable is thermally limited, which you would see here by a maximum temperature of the cable reaching 70.
So the cable conductor is operating at its maximum value of 70 degrees Celsius. It's not being limited by electrical stress. Can we look at the soil temperature plot just out of interest? So what are we going to vary here?
So now we are going to increase the pole separation. Yeah. So from 0.3 meter to be separate, increase the pole separation to 1 meter, and then see the dictating factor is now temperature drop across the insulation. So you can see that now the cable has become stress limited as we increased the separation. The mutual heating effect has reduced. So the cable temperature does not reach the maximum allowable limit of 70 before the drop across insulation reaches its limit of 10.7. This has become
It's
it
now
has
it's
become a
not
stress limited now.
it's not operating at 70 degrees Celsius anymore. Mutual heating, which is a thermal limitation, is not the dictating factor. Now it's electric stress.
Yeah, it
We're
is.
running out of time, Omer, so we've got to speed it up.
Okay, so if we go to ducts, so if we enclose the cable in ducts, you can see that the cable has become thermally limited. The dictating factor it is now temperature drop across insulation is false, which means
The
that
current rating
it
has
has
gone
become
down.
thermally limited. Yeah,
Current rating has gone down, and
yeah,
now the cable it's gone from stress limited to thermally limited
thermally limited.
because of the
Yeah,
ducts.
yeah. If we remove the ducts, it is stress limited again, and if we get to the soil dry out, it becomes thermally limited again.
Yeah.
So what, and also with the depth, if you increase the depth to it, it's at lower depth, it's stress limited. If you increase the depth, it is likely to be thermally
Thermally
limited.
limited.
So as what we conclude from this demo is that enclosing the cables in duct, soil dry out, and greater burial depths lead to current ratings dominating the thermal limited ratings dominating the effective current ratings.
Thanks, Omer.
So
So when we talk about buried cables, there are, the typical factors affecting the current rating. So you should consider that burial depth is going to reduce current, higher burial depth is going to reduce current rating. It's also proportional to soil thermal resistivity. When you install HVDC cables in ducts, we saw that it reduces the current rating. You can consider that, the fill material of the ducts also affects the current rating. You can modify that to be air or solid filled or even water filled. If you're burying HVDC cables at great depths, you should calculate the actual soil ambient temperature rather than assume something conservative. You should always assume or consider soil dryouts, perhaps of the native soil. It has a significant effect on the current rating. And for more complex arrangements, such as this ducts inside a pipe, which can sometimes be used for offshore landfalls, you'll need to use FEM. You can't do this sort of installation calculation using the IEC calculations. So here we see that how the effects of burial depth on the current rating. I'm going to sort of whiz through this stuff. There's a lot of in it. But what we saw with OMED was that for shallow buried HVDC cables, the cable is stress limited, so the rating is limited by the electrical stress. And as we move the cables deeper to a greater burial depth, the current rating will go down as the cable becomes thermally limited. And here we have a bit of a comparison with FEM as well. You can perform buried calculations or these HVDC buried installation calculations using the IEC, or you can use FEM. You can consider isothermal or ideal ground surface conditions or non-isothermal. When you consider non-isothermal, you are considering it's a more accurate calculation. You're considering convection or heat transfer between the soil and the ground surface. And in general, you'll see a lower current rating for FEM current ratings as opposed to pure IEC. So bipole separation, when we separate we also saw that with OMET as we vary the separation of the poles of the HVDC system, we affect the mutual heating. Now, poles that are closer together, the cables are more likely to be thermally limited as opposed to stress limited. The same is true if we enclose the cables in ducts or they're directly buried. Uh, um, Direct buried cables are more likely to be stress limited, and cables in ducts are more likely to be thermally limited. The current rating of HVDC cables in ducts is generally lower. Okay, so soil dryout, a very important factor. Obviously, this increases temperatures of the HVDC cable systems. So the cable system is much more likely to be thermally limited. Temperatures go up, current ratings go down, electric stress limit becomes less relevant when you're talking about soil dryout. You can see the plot in the bottom left and the bottom right hand corner. You can see with and without soil dryout while operating at the same while carrying the same current. So if that cable system is carrying the same current, you see much higher temperatures when the soil dries out. In our software, you can just turn soil dryout on or off, and we've extended the IEC calculations to allow you to consider soil dryout for multiple buried circuits. We were going to cover a ventilated tunnel installation, but I don't think we have time. I think it's probably better that we do a quick FEM calculation with Edson. I think it's going to be more interesting for everyone. But this is a typical. So we've covered three of the most common typical installations for a HVDC cable system, right? So first we covered an air-filled or unfilled trough that's relatively common, but HVDC cables in tunnels, very common, a use case. And then buried HVDC cables, obviously very common. So these three installation conditions are very common for HVDC cable systems. That's why we covered them. So I've got a few tips here when you're dealing with cables in tunnels. Tunnel air temperature often Tunnel air temperatures are often much lower than soil temperatures. So soil drying doesn't usually need to be considered when the cables are in the tunnel. High surrounding soil or tunnel air temperatures reduce current ratings. Tunnels with many circuits may require ventilation. Soil thermal resistivity affects the current rating. So the soil surrounding the tunnel affects the current rating of the cables in the tunnel, but not as much if the tunnel is well ventilated. Here's some plots of tunnel length, depth and length versus HVDC current ratings. So the tunnel depth has a little effect on the stress limited current ratings. For 1 kilometer tunnels, so reasonably short tunnels, a depth increase of your tunnel, a deeper tunnel, causes negligible change in both stress limited and thermal limited ratings. So short tunnels don't really, varying the tunnel depth doesn't really have a big impact on your current rating of HVDC cables. However, for long tunnels, increasing the depth does have a reasonably significant impact on the thermal rating. So the HVDC cable in a deep tunnel or a long tunnel is more likely to be thermally limited. And as you make the tunnel deeper, it's going to be more thermally limited, or the current rating will go down. Airflow inside the tunnel. This also depends on the tunnel length. As air velocity increases, so from relatively still to a reasonable flow, stress limited ratings govern uh, uh, over thermal limited ratings uh, for longer tunnel lengths. And for lower air velocities, so when there's less airflow, the cables are more likely to be thermally limited for obvious reasons. Like I said, it depends on the tunnel length. It's related to tunnel length. Let's look at an interesting example of modeling a HVDC cable system in a pipe using ELEK Cable HV FEM software. Let's do it for 5 minutes. Then I'll give you a link for a certificate. We'll draw some conclusions and we'll get into some questions, Q&A for say 10 minutes. I'll hand it over to Edston now. Thanks, Edston.
Thanks, Jason. Okay, so let's go on from where we started. So this is the same cable that we designed. It's a 320 kV cable, 2000 square copper conductors with 70 degrees as a maximum conductor temperature and 10.7 as a temperature drop across insulation. So the same cable, it's kept at 0.1 and 0.7. So what I would do is I want it at a 1 meter burial depth. So I keep it at 0.1. It's in flat arrangement. The depth reference is top of cables. Let me do it as center of cables because that's what normally we use. Now, as Jason showed you, what we are trying to do is we are trying to put these two cables in two separate ducts and then enclose them in an HDD, which is filled with some solid filling material like bentonite or concrete. So to do that, what we do is I have specified a thermal resistivity of the surrounding soil as 1 Kelvin dot meter per watt, a soil temperature of 20 degrees. I will do isothermal for the time being, but there are other options which you can specify for non-isothermal conditions, the air temperature, etc. But it takes a bit more time than the normal isothermal calculation. So I will do for the example, I'll do isothermal for the time being. I will add ducts to it. So I'll add a duct. This is how we add ducts in cable HV. So the duct is assigned to the circuit. So circuit 1 has a duct. The duct is pretty small, so I can make it a bit more larger to fit in the cables. So 175, for example. So now the cables are in a duct. Now, if I want, I could go back to the circuits and change the depth of reference. So now it's center of cables. I can make it center of ducts. So now the center of duct will be at 1 meter from the ground. So this is a duct. The duct is filled with air. We have a list of materials for ducts, PVC, PE, asbestos, or custom also if you would like to. Let me take PVC for the time being, a duct, and the duct is filled with air. Now, around these two cables and these two ducts, I am adding another duct, a bit more larger one. So let me add a duct. Now this duct is going to be an empty casing for the time being. We can using the mouse, we can increase the diameters. We can change the positions by dragging them inside. So for example, because I know some parameters, let me make it 0 and 1. Let me take it as a larger pipe, about 800 mm and 704 mm in diameter. The duct is PVC duct. Let me fill it with a solid material like bentonite or something with a thermal resistance of 0.6 Kelvin dot meter per watt. So this is my arrangement. Now I can go forward and calculate this. Shouldn't take much of a time, around 2 to 3 iterations would be enough for this. Should be solved under a minute. Yeah, so this calculation also take into account your temperature drop across the insulation. We could see whether the cable is thermally limited or stress limited. And we could have any kind of installation in this, which is including multiple backfills, multiple troughs, multiple circuits inside one duct, circuits partially in a duct, or you could have a large number of circuits in a pipe. So yeah, so that's the peculiarity of FEM. You can do anything that is not done in IEC. You could do everything in here. So as we calculate, we show you the iterations count. So we have done the calculations now. It's only about 3 iterations. It is not thermally limited now. The current rating is around 1606 amps. As
Oh,
per
no,
TB880 and other.
it's not stress limited. It is
It's
that
not stress
number.
limited. That's mainly because we have filled it with solid. If you're filled with air, it'll go back to stress limited. We have rounded down the current ratings here as per TB80 suggestion. Someone asked a question in the chat. I believe that why do we do it? But this is because of TB880 assuming that the diameters or the thermal resistance may not be accurate. So just for a safety side, we just reduce the current rating to the nearest value depending on the value of the current.
Can we see the mesh
So
plot and then we'll go to some questions, I think.
yeah, the mesh plot.
Is there anything
I
else
will
you
bring
wanted
up
to say?
Yeah, I'll bring up the mesh plot. It takes a bit of time because what we are doing is, I mean, in this example, you would see at least 100,000 meshes because our soil area is very large. So it takes a bit of time to plot
Mm.
all the individual meshes and individual temperature points. That's why it takes a bit of time. Um,
Okay.
but I think
Why don't we go to Q&A or something? Is there anything else you wanted to say?
no, that's all I wanted to say. Yeah, I think the temperature plot, the mesh plot is something what you have showed Jason on your
On the
presentation.
slide,
It's the
yeah,
same
yeah,
on
yeah.
the slide, so it's the same thing that's going to come up here.
You can see the mesh plot
Any
here on the slide.
yeah,
Um,
any conclusion that we have to draw, and then we go to questions.
yeah, there is, yeah. So let's talk about some conclusions in brief, yeah, and maybe you can collate some questions. So let's remember that HVDC current ratings are limited by thermal and electric stress constraints. Stress limits often dominate, especially at higher operating voltages. You could increase insulation thickness or allowed electric stress. This could significantly boost ampacity or current rating. Thermal limits dominate for deeper buried cables in duct installations or where soil dryout occurs. Stress limits dominate usually in air or at shallow burial depth. Effective ampacity is highly sensitive to installation design such as burial depth, soil properties, tunnel ventilation, and separation, which all must be optimized. That's pretty typical of AC or DC. Yeah, as was already shown, soil dryout greatly reduces current ratings for buried cables. You should always consider soil drying for buried cables, not necessary for tunnels. For tunnels, short tunnels, cables are usually stress limited. For long tunnels, they become thermally limited, and you should consider the air velocity effects, which could have a significant impact. It's recommended that you carefully evaluate all installation conditions along the entire HVDC cable route to identify thermal bottlenecks. I will now share in the chat a link uh, where you can fill out a form and make a request to get a certificate of attendance, perhaps for CPD points. That will be emailed to you in the next couple of days. So find that link in the chat in the next minute or so. So it's then we can answer a few questions, I guess, while I get that link and
Yeah, yeah. Okay, so let me ask you a few questions. Now, how common is HVDC in Australia? Are we using it in submarine cables somewhere in Australia?
yeah, I think it's common. I don't know about saying it's common, but we do have HVDC cable systems in Australia, and the Marinus Link, I think, is the latest one, which is crossing Bass Strait again between Tasmania and Victoria. I don't know the current status of that. I think this design has been completed. I think there are others on the call who could answer that better than me. But yes, we do have HVDC in Australia and New Zealand.
The other question is, uh, what is the different bonding types and their advantages and disadvantages?
That's not really relevant for this discussion on HVDC.
Uh, how do we determine, or what is the right assumption for thermal resistivity when we use HDDs? And can we consider seasonal variations?
What is the
What is the right assumption for the thermal resistivity values when we use horizontal directional drilling? Something with like conformal mapping thing, I think.
yeah, I mean maybe you could talk about thermal mapping. I'm just trying to get this link.
So when in the case of HDDs, you would cross many layers as we go through the layers of soil. So there might be different thermal resistivity. So what we are not doing it now, but we are coming up with an algorithm which can give you an effective thermal resistance for the soil. It's a method which is called as conformal mapping. So using that, you can come up with an equivalent soil model when we want to do an HDD installation. Now, along with seasonal variations, we have not done anything on season variations, but what we would recommend is to use the worst case thermal resistivity if that is known. You can do measurements and then you can take the worst case thermal resistance of the soil. Um, the other question is, do we support hybrid systems, AC and DC cable in the same trench? Yes, we do. You can have AC and DC cables together. If you use FEM, you can even have them in the same duct. But in the other IEC methods, we can support hybrid systems for direct buried or in ducts. Um, now multiple circuits, mutual heating, how are they accounted for? So each cable each cable in a circuit is assumed to be heating the other cables in the same circuit, while or the other cables in other circuits also. So multiple circuits mutual heating is very important factor that has to be considered. We have seen a 10 to 15 degrees temperature rise because of mutual heating between cables, especially when cables are very deeper. So we in our software in cable HV, we always consider mutual heating between circuits. But if in case you would require a rating without mutual heating, we have also an option to select that, where you can ignore mutual heating and get the ratings. But always it is unequally loaded cables, and you can get their ratings.
I've shared the sorry, my computer, because it's recording directly to my
Yeah.
computer. I've
Okay.
shared the survey link in the chat. Hopefully everyone can see it now. Uh,
Yep.
like I said, please fill out the form, and you'll get a certificate of attendance. Uh, Anything else, Edston? Should we?
No. One question on FEM was what difference do we expect to see between isothermal and non-isothermal?
What's the answer there, Edston?
So what I would say is depends on the depth where you bury it. So if you bury it very deep,
Mhm.
for example, if you go to 3 meters, 4 meters depth, you will practically see no difference because non-isothermal conditions become isothermal when you go to a deeper cable. But if you are burying very shallow, for example, 0.1, 0.2 meters below the ground surface, you will see a significant difference. We have seen more than 10-15% difference of cables between isothermal and non-isothermal conditions. So yeah, so if it's shallow buried, always we use the isothermal process.
Yeah. Thanks so much, Edston. We'll wrap it up there. Thanks, Omer. Thanks so much for your help, guys.
Thank you, everyone.
Pleasure as always. Thanks everyone for attending. It's been a really great presentation, I think, and we look forward to presenting again to you guys soon. Look out for the next technical webinar, which should be in the next few weeks. We hope to see you again. Thanks, everyone. Thanks, guys.
Thank you.